Alright, let's continue our discussion with fluids by talking about now fluid dynamics. So when we say fluid dynamics, before we had fluid statics, right, everything was sitting still, right, we just had these kind of still bodies of fluids, right, and we were just calculating, various quantities from them, mostly dealing with our pressures, our densities, and our buoyant forces and all this kind of stuff. But now we're going to talk about fluid dynamics, where we have fluid flowing, right? We have some sort of fluid flow. You can imagine this as like water flowing through a pipe, or like water flowing down a river or something like that, right? But the important part is we have some sort of contained path that our fluid is now flowing through. So the thing that we're going to have to talk about first is our Q, which is kind of our amount of fluid flow, right? So Q is going to be in terms of volume per time, right? So this is not speed, this is supposed to be a capital V, right? This is volume per time, right? This is kind of our rate of fluid flow, right? How many, standard units would be in liters per second, right? So how many liters of water per second, or whatever fluid you have, are flowing past, flowing through your pipe that you have. So we can kind of visualize it. We can actually write this in a little bit better way. So let's say, right, here's our pipe. We have some sort of fluid flowing through it, right? Let's focus on this section of fluid right here. So one other thing that's important to note, we're going to, for our cases, assume that this Q is always constant, right? So no matter how much we have, the rate of fluid flow is going to remain constant. We're not ever going to change this Q. We're going to have a constant amount of liters per second that are passing by through our pipe, right? Let's just isolate this chunk here of fluid as it's going through the pipe, right? So as it moves down in this way. So we have some area here to this, right? The area of the pipe, or in this case, that also corresponds to the area of this little kind of isolated cylinder of fluid that we're talking about. And so, of course, this distance is also going to correspond to again, just this chunk of fluid that we are following, right, as we were flowing down the pipe. The fluid is flowing through the pipe the whole way, but we're just focused on this, isolating this little chunk. So what we can do is we can actually write this in a different way, right? Our volume is actually equal to the area of the pipe times that distance, right? So let's write our Q in a different way now. We have Q is equal to A times D over T. But what is this D over T, right? This is still a distance, right? This does correspond to our volume, that is A times D, but D over T is the speed of the fluid, right? The speed of the fluid as it's going through here, right? This distance here, however long it takes for, this chunk of fluid here to pass this distance, right? That will tell us the speed of this fluid flow. So we'll have A times V, right? So along with this, we can see that if we have constant fluid flow, right? So this Q is constant. What happens to this A as our pipe gets narrower or wider, right? Let's say, we end up with a wide section of pipe and then like a very narrow section of pipe or something like that, right? You can think of it as, again, like the river as it's flowing getting wider and then the river getting narrower or something like that. If this Q has to remain constant and this A changes, what we see is that, this might be a somewhat intuitive result, but we can see right away that as the pipe widens, right, our speed must go down, right? We have bigger A, so we have a smaller speed, right? To maintain this same Q, right, it doesn't have to move as fast, right? Because there's more, there's more of it, spread out across this wider area that we have. Of course, then if we do the other thing, right, if this path gets narrower, right, then the fluid must speed up, right? The speed must increase. And that's going to be kind of very important to remember, right? Just kind of build our intuition of how this stuff is flowing through. If it widens, it slows down, right? And then, of course, again, if you ever, gone down by a river or something like that, you can see this happen in real time, right? When it's very wide, that's when it's moving very slowly, right? And when it's very narrow, it's going to be moving a little bit faster, right? Again, it's all because this constant fluid flow, this constant rate of flow is actually also a pretty good approximation for a lot of situations that we're going to run into. So this is one way that we can kind of mess around with this, right? We're going to have it flow down this pipe, but we can also have this pipe get wider, or we can have it get narrower, and this will change our speed. Another thing that we can do is we can actually have our pipe either go up in height, right? It can go up like away, up as in, the opposite direction of gravity, right? Up away from gravity, or it can go down, right? And this is also going to change some of the internal workings of exactly what is going on here. What we're going to see is that it'll actually change the pressure within the fluid in this pipe. So let's take a look at that, right? Let's take a look at an example of this. Let's say that we have a section of pipe that looks like this. It starts out very wide, and then it goes up, and it also gets very narrow. So now we're changing two different things at the same time, right? So here at the bottom of this pipe, we're going to have some sort of pressure. We're going to call it P1. We're going to have some sort of we're going to have some sort of speed, V1. We're also then going to have some sort of height, right? We're going to call H1, right? And so we know, obviously, as we said before, right, our pressure is going to vary with this height, so that's also going to change some of these other things we have. So you have some sort of pressure in this fluid as it flows through here, right, as it's moving this way. We have we're moving at some sort of speed, and we are at a certain height, H. When we get to the top, we're going to have a P2, we're going to have a V2, and we're going to have an H2. And what we actually have here is essentially going to be a conservation of energy equation that we're going to be able to write. And it's going to be called Bernoulli's equation. I'm not going to go through the full derivation of it. I will link a YouTube video. It's very important to understand where it comes from. But there's a wonderful YouTube video. Someone explains where it all comes from much better than I can. So I'll link that. I'll have that embedded beneath the video here on Canvas as well of my lecture. But here's how we can relate these two situations, right? So here we have, again, fluid flowing. It has some pressure, it's flowing with some speed, and it's at a certain height. As it goes up, it gets higher, something's going to change, right? Some of these values are going to change, as we can imagine, right? The pressure might change, the speed is definitely going to change as this pipe has gotten narrower, and of course we can see, obviously, it's gone up, so the height has changed. So how do we relate all of these? What I'm going to do is I'm going to write an equation for you again. It's called Bernoulli's equation. Make sure I spell this right. Bernoulli's equation, and it's going to look pretty familiar to you at first, but it's going to be a little bit different from what you've seen. So what we can say is this. We can say P1 plus 1/2 rho V squared plus, V1 squared plus rho G H1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. So, which of these terms look familiar right away? We've seen this one before, right? We see all this just in chapter 11, right? This is our pressure due to just being at a certain depth below the surface of our liquid, right? Of our fluid. So this is rho GH, but also we're going to see, as I said before, it is similar to mgh, right? But this is a pressure, it's not an energy. But what are we really looking at here, right? We also have this term as well. This looks similar to our kinetic energy term. This looks similar to our potential energy term. This looks similar to our kinetic energy term, but there's something different about them. Instead of m, right, what we have is rho. We have the density of whatever fluid is flowing through this pipe, right? So we have this rho, right, which, as we know, is just mass divided by volume, right? And so, of course, the pressure here as well, what happens to this equation if we just multiply the entire equation by the total volume of fluid that we have? Well, what you would get is PV plus 1/2 mv squared plus mgh, right? And at that point, you would have an energy equation. But what this is, we've divided that energy conservation equation, right? We are just conserving energy, right, as we go through this pipe, right? There's just the extra term of P here that I'll explain in a minute. And what we're doing is we are then dividing by the volume. So what we actually have is an energy density equation. So we're having energy per unit volume is what we are conserving in this case, right? Okay, so what we have then is we have this equation here. We have our 1/2 rho V1 squared plus rho G H1 plus P2, equals P2 plus 1/2 rho V2 squared plus rho G H2, right? So these terms you're familiar with seeing, right? This is our kinetic energy density. This is our gravitational potential energy density, which it turns out the energy density does have units of pressure, right? So if you were to multiply this by V, you would get an energy, but what we're saying is that essentially there is some sort of energy associated with the fact that there is an internal pressure in this fluid, right? So these two terms are the terms we're used to. This is associated with the bulk motion of the fluid. This is associated with the gravitational potential energy of the fluid. But these pressures that we have, these extra terms that we have, are saying that there is also some energy contained in the fluid, just from the internal pressure of the molecules all bouncing around on each other, right? So that's kind of the extra term that we have. But sure enough, just like our energy conservation equations, if I give you the initial conditions here, right, then as far as what the pressure, the speed, and the height of this pipe are at this time, as this pipe widens or narrows, right, as we move along, maybe you'd need to see exactly what this area is to figure out what this V is, but you could, sure enough, you could calculate what these other values were, right? You know that this, all these three terms together, the pressure plus the kinetic energy density plus the gravitational potential energy density, all of these together have to add up to be a constant value, right? This is what allows us to write our very similar, very analogous conservation of energy density equation.